even into a Wednesday, maybe for most of chapter 7. I don't know how deep the math is going to get. Here's the. So we're going to look at Raoults Law and then combine it with Dalton's here in a minute. I put these up on the board because I think the challenge is going to be to not get lost in the symbols that are going to be used in the next 40 minutes here. Okay, don't get lost in the symbols. We're going to be looking at chemical potential a little bit to derive some really simple equations. It's going to get a little muddy, and we're going to come out into a really clear space with some really pretty simple, straightforward equations. Okay? So bear with it. And as a matter of fact, as I go through it today, I'm going to kind of show you the end equation. Here's where we're going. Here's Raoults Law. Now let's see, where did that come from? And we'll end there. And then here's Raoults Law with Dalton's Law combined. Here's what the final equation looks like. Now let's see how we get there. Okay? So here's chemical potential activity. This is going to be mole fraction. The mole fraction in solution. This is going to be mole fraction in the vapor phase. Okay? So we're not going to use all of them in the very first equations. It's going to be fairly simple. But we're eventually going to be getting all these things kind of related to one another. So mole fraction in the solution, mole fraction in the vapor phase. This is going to be the vapor pressure above a solution for a particular component. 1. What is this going to be? This is going to be the vapor pressure. So see, this is not a knot. It's a asterisk, kind of. This is going to be the vapor pressure of component number 1. If it was pure, if it was the pure component, though it wasn't in solution with anything else. All right, so that's its vapor pressure at whatever temperature you happen to be at if it was there all alone. And this is going to be its vapor pressure if it's in a solution with something else. And P2 likewise. Component 2 all by itself. So I didn't write out the definitions of all these, but it's kind of what we're looking at. So just pay attention to what the symbol is relating to and try to follow it as we derive the equations. I got it.
Getting into Clarion properties,
Clarion properties?
Colligative.
Colligative, yeah, colligative.
Okay.
It'll eventually get the colligative properties. Right. It's going to relate a lot to distillation. It's going to, azeotropes, are you familiar with azeotropes? That there's some things that are really hard to distill out of other things because they actually form an azeotropic combination that it's hard to distill alcohol down to 100% alcohol because you get a little bit of water, you get an azeotrope formed, and there's about 5% water is coming up with it. So fractional distillation. If you drive by, the chapter has pictures of labware, and it does have pictures of industrial things. So, I said I came up here from Texas. You drive along the Gulf Coast, down near Corpus Christi, all the way over to Houston. And in Houston, that was one thing I was going to mention the other day. There was a major fire in Houston. Did you guys catch that on the news? Mm-hmm. Huge fire. Burnt for 5 or 6 days. It was a big inventory of volatile products, gasoline, diesel fuel.
Oh, I did see that.
Yeah, it burnt for 4 or 5 days. They closed down schools. They evacuated areas. They were pumping carbon dioxide foam on this fire for 4 days, continuously. And then even that, I think after the fire was out, and this was last week sometime, they continued doing that for another day or two. They said, we got to get the temperature of all this metal down to below the auto ignition temperature of these volatile compounds. There was huge tanks of this stuff still sitting around this huge fire. There was a lot of stuff that could have burned there, and a lot of stuff did burn.
Was there anybody there, like in there?
I don't know. I never heard of any death toll. There was major concerns about the effluent that was coming out, the smoke, and then the volatile organic compounds that were, in the air everywhere. But back to the point. You drive along there and you see these columns, white columns going up, and those are basically distillation, fractional distillation columns, which will relate to this chapter, where they're taking off IPA and they're taking off ethylene, propylene, butylene, all this sort of stuff. They're fractionally distilling crude oil to get all of the different volatile compounds out of it, pure, and then you take them off. I mean, a big chunk of it is going into gasoline and aviation and diesel fuel, but then all the plastics, okay? And you take certain cuts off at certain levels. The ethylene is going up to the top of the column. It's got one of the lower boiling points. The gasoline is coming out somewhere else along that column, and they may even go through the methane for natural gas, pumping it into natural gas tanks. Have you ever gone by any of these places and you've seen that you drive by them and there's a big tower going up with a big flame shooting out of it? What's coming out of there? Natural gas. And if you think about it, if you have a gas-fired hot water heater at home, most of them now are electronically ignited, but 20, 30 years ago there was a pilot light in there. And when I had a home with a hot water heater light with a pilot light, I always felt good when I could see the pilot light was lit. Because if the pilot light goes out and you have a leak, a natural gas leak, you have the accumulation of natural gas to a point where it will explode. But as long as you have a pilot light, you're not going to get an explosion. It's just any methane that ventures into or near that pilot light just burns in the pilot light. So these big places, they have these flares going there, and that's so that you don't have a big, huge cloud of methane or something accumulating around these places that all of a sudden explodes.
Also, like protecting the tank.
Well, protecting the whole facility from, a static spark that just ignites a big cloud of stuff. When I was at, Dow Chemical, in some of these plants there, they have cars to drive around in the plant. They're not allowed to have catalytic converters on them. They take catalytic converters off those cars because the catalytic converter on your car is hot. It's igniting all of the kind of the crummy molecules, the sulfur and different stuff that's coming off of your exhaust of your engine. It's running it through the catalytic converter and oxidizing all that stuff, and so catalytic converter is actually running almost hotter than your engine. So they would take those off of there. They would just exhaust it. They didn't want these sources of ignition.
Is that legal to take off the catalytic converter?
They probably had to have a permit to do it. And it was a car that was dedicated for running around inside that facility.
What's bad about not having it?
Well, because you put off a lot of CO and other stuff that's kind of poisonous.
Yeah, so they probably had to have a permit, but for safety reasons, I'm sure they could probably get that permitted. Okay, here's a question for you. Let's say we have two containers here, and this one has it's 30% IPA and 70% water. Isopropyl alcohol. And here, this one is 70% isopropyl alcohol and 30% water. This is just a hypothetical. What do you think the composition of the vapor above these two solutions is? And I mean, don't give me an exact number. Do you think the concentration of the solution is going to affect the concentration of the vapors above it?
Yes, but not as much as it actually.
Because the azeotrope is formed, I don't think it will affect it. Or
The IPA
it might to some extent, but not very much.
Okay.
I don't know.
Well, I just asked the question because as we go through here, these laws are gonna more or less answer that question for us. Yeah, we'll see. So, in other words, what would be the vapor pressure of the IPA above here? What would be the pressure of the vapor pressure of the water above here? Would the vapor pressures be in that same ratio of a 3 to 7 ratio, or what would it be? So let's just, and then just one other question as we get starting, and I didn't think of this until you were mentioning this infrared. Have you guys worked with GCs to any great extent? Gas chromatographs?
Yeah, I have.
Okay. Well, gas chromatographs are kind of doing on a very small scale fractional distillation. You can shoot a sample of gasoline into a GC, and what you will get out of it is you'll get a gas chromatograph that kind of looks like this, and it has a peak for every component that's in the gasoline. So if gasoline is predominantly octane, you'll get a big, huge peak for octane, and then you'll get peaks for all the different isomers of octane. There's some heptane in there, there's a little hexane in there, there's some nonane, decane, all those things will be separated out by the gas chromatograph. So it's a chromatographic technique, and for the oil industry, for the chemical industry, it's a workhorse. You say, hey, I think this is pure. Well, get me a GC of it. You find 6 peaks in there. It's not pure. There's other stuff in there. Or only 30% of the sample comes out. And you say, well, there's 70% of something in there that is really not, it's got a very high boiling point, or is getting clogged up on
So
the...
you won't see everything, you just see the volatile.
You'll hear the volatile stuff. Right. So the stuff that really has a really high boiling point or is gummy will just get clogged up on the column.
What sort of boiling point will not really show up past that, you know? Sure, anything over 200.
Well, these things are boiling points under 100. You could get some things out if they're not going to decompose first at 300, 400 degrees. You're running nitrogen. Nitrogen is the gas that's pushing everything along there, and so it's not being oxidized. But if you get up too high, then the molecule probably starts falling apart. But I've done thousands of GCs, but I kind of forget. You would program your column up from maybe 50 degrees C up to 400 degrees C, and you'd be baking stuff off of there. Okay, well, let's start chapter 7 here a little bit more. In chapter 6, we had that simple equation for degrees of freedom, just 3 minus the number of phases, as we talked about a little bit more. I'm not going to concentrate on this too much, but as we go into a multi-component system, we're going to adjust this a little bit. degrees of freedom now is going to be the number of components minus the number of phases that you're dealing with plus 2. All right? And without dealing with that too much, let's just look at this example from your text. Consider a mixed drink that has ethanol, water, and ice cubes in it. Assuming that this describes your system, how many degrees of freedom are necessary to define your system? All right, so there are 2 individual components. C. C is 2, excuse me. C is 2 because you got water and ethanol. You have 2 phases. You've got water and ethanol in the liquid form, and you got ice cubes in the solid form. So you have 2 phases. So 2 minus 2 plus 2, there are 2 degrees of freedom. So big deal. Well, this goes on to say, just kind of looking at that, if the temperature is specified, if you're given the temperature, now you only need to be given one other thing to define the system. So you got a temperature, let's say, and let's say you're given a certain amount, the mass of this system, or the mass of water, or one other component in the system, and you would actually have defined enough things to ferret out a lot more information about the system. So practically, how does this help us? When you're given some of these problems, like even some that were on the exam, you're given problems, you're given a bunch of information, and you're asked to calculate something, and you say, well, I don't have what I need here to calculate this. So you start asking yourself, do I have information here to calculate something else that gets me one step closer to what this problem is asking for? Do I have enough information here that I can elucidate everything else about it, including what I'm being asked here, based on this information? And I've used this example before, which it's maybe a simpler way to look at this. We know that we have four parameters here that need to be described to explain an ideal gas, but you only need to know 3 of these to determine the 4th one. You don't need to know all 4 of these things. You know any 3. And you don't even, in some cases, you might not know the moles, you might know the grams, which is a step closer then to the moles, gets you to there. So, that's kind of what we're looking at here. You might have a complicated system, but there may be enough interconnections between it that it can be described fairly easily. Okay, so let's take a look at Raoults Law here for a second. I would love to go paperless, but I can't imagine it. I don't know. It's probably a generational thing. What do you think? Okay, so see, pretty simple equation right there. We're going to solve some simple problems with that. Raoults Law, that the partial pressure of component I above a solution of this stuff is going to be equal to the mole fraction of I in the solution times the partial pressure of it if it was pure. There wasn't anything else there. Okay, so let's just walk down through how did we get to that Raoults Law. And we'll just start with the chemical potential of I is at equilibrium. Now we're talking about equilibrium again. The chemical potential of component I in the liquid phase is going to equal the chemical potential of component I in the gas phase. Remember, if you're at equilibrium and you have these two phases in contact with one another and they're at equilibrium, their chemical potentials have to be the same. That's back in, I think, chapter 5. And then this is going to be a little lengthy, so let me just run through it real quickly. The chemical potential of the gas, and why do I have the gas over here? But I do, is of the gas at whatever temperature we're working at is equal to the chemical potential of I at standard conditions times RT over, oh no, there's fugacity. We don't like that.
So how do we know when the little f is degrees of freedom and when the little f is fugacity? Because it stands for both, and it just kind of just decides where it wants to show up.
Well, okay, let's...
Well, it's overpressure in this one. So.
Yeah, it's overpressure in this one. Context. We're gonna have to rely on context.
Yeah. Because the other one we don't really use.
Like when
I ever use degrees of freedom in equations, or is it just to determine?
Probably not.
How many phases are
it might be how many degrees of freedom are in this system, like that problem.
Yeah, like.
So F equals. I mean, F also means force. Capital F is force.
Yeah.
So in the context right now, we're kind of there just aren't enough symbols for all the different things we're talking about. Good question. Okay, now, all right, we won't get down in here too much, but for the gas, it's going to be the mu I at standard conditions plus RT. I think that's supposed to be, I'm sorry, there's supposed to be an ln in here. Sorry. Have I taught you yet to work in pencil?
Yes.
Good. All right, good. So if that is the case up there, then we can set this equal to that. We can set those equal to each other. So we can come down, so we have this expression is going to equal, this is the gas, this is equation 7.9, by the way. So if we only had one component, just for a minute, we only had one component, then mu I of the gas I think we're assuming two things here. If it's one component and basically ideal, then we're going to have the you can get to this point where you can get rid of the fugacity. So we mentioned it, it entered the stage and left, it had a bit part in here. We're going to let the fugacity leave, and we're going to be talking about the vapor pressure of component I if it was pure, if it was the only thing there. And then if you go one step further, take that star off of there. You can get expression like this, and these two things will cross out, and you have RT
And then all RTs cancel out.
ln pi over p naught equals RT ln pi star over p naught plus RT ln ai. Yeah, all the RTs will cross out, and you'll have the ln of pi over p naught minus the ln of pi star over p naught equals ln of ai. That's the activity of the liquid. So
on the left side of the equation, where did that natural log come from? Was it supposed to be up in the...
yeah, it was supposed to be up in here. Yeah, that's where that came from.
And where did
Oh,
the
that should have been
asterisk
the whole
go?
time.
Yeah.
The asterisk here moved over, this asterisk moved over to this side of the equation. So if I get rid of all these RTs,
You put the pi over p naught. Up there, you have RT times pi asterisk over p naught.
On the bottom one?
Nope, on the very top, under form 1 component ideal.
Oh, how different signs are you in?
Yeah.
It didn't really... so there's two different equations in this one, I think, and then he just...
yeah, what I'm doing here, okay, Liz, what's happening here, you see, if we only had one component, we'd have this equation here. So what I'm doing is substituting this for that.
Oh, okay, I see what you did.
Okay?
Yep.
Okay. Sorry, that's what I'm doing there.
Gotcha.
So we're going to substitute that into there for that. And that's where we get this long equation. And so this is this is kind of the ln of pi over p naught times p naught over pi star. Okay, you can take this out of there by reversing that and multiplying those together. Right? This is going to cross out, and so then ln, the natural log of pi over pi asterisk equals the ln of ai. And then if you just kind of take the analog of both sides of this equation, you get down to here.
You're right.
And you can get to this point where the partial pressure of I is equal to the mole fraction. What's its activity? It's related to its mole fraction times what its partial pressure would be if it was pure, if its mole fraction was 1. Okay, because if xi equals 1, in other words, it's 100% I, then pi equals pi asterisk. Now the other thing to just kind of keep in mind here is that this is basically, this follows the pattern of an equation for a straight line, where xi is the slope of that line. Yes?
So where did AI go and where did XI come from?
Well, AI is, I don't know if would say it's proportional to its mole fraction or actually equal to its mole fraction. Its activity is related to its composition.
We're making like an assumption or like a, right? I mean, is it actually equal or?
In the equation, yes, we're saying it's equal.
Yeah, but if we go back to like chapter 5, some of the equilibrium stuff, they have like this gamma or y times, or so activity equals like y times, is it molality or something like that? It's some different. It's not like, I don't know if it's actually like they probably say in text.
Yeah.
Assumption.
Yeah, we could go back and look at it.
I'll see if I can.
And this may be looking at it as not in terms of concentrations, but actually just mole fraction.
Yeah, they say AI equals gamma I times molality I over 1. This is 5.17.
Where are you?
5.17.
What page is it?
131.
5.17. See page, for what? For this is the relationship of activity
and molality. It doesn't give us mole fraction, but molality.
Okay. All right. Let's just kind of put that in the bin to ferret that out a little bit more. But this is Raoults Law right here. And let's apply it right here. Okay? So here's an ideal solution, can be approximated using the liquid hydrocarbons hexane and heptane at 25 degrees C. Hexane has an equilibrium vapor pressure of 151.4 millimeters mercury. Now this is going to be, how would you label that 151.4? I mean, how would you label that with relationship to these pressures? It says if you had hexane at 25 degrees C, this is what its vapor pressure would be at that temperature. Okay? So this is vapor pressure of hexane. It's going to be with the star on it. If it was pure hexane. Okay? So in these problems, what you really need to do, and I really do suggest, if on a test, a problem set, whatever, you have a word problem, label the data. Scratch on out there. This is what this is. This is the partial pressure of pure hexane at 25 degrees C. Heptane has an equilibrium vapor pressure of 45.7 millimeters of mercury. This is going to be the partial pressure of pure heptane.
Do we have like a table in our book to look these up, or are they normally just going to be given?
Probably in a problem like this, they'll be given. I don't know. I was looking at the text problems at the end of the text. You might have to look some of these up. but I don't know where they are in the appendix. What is the equilibrium vapor pressure? Okay, so now they want to know the equilibrium vapor pressure. Okay, now that's not going to be the vapor pressure of hexane or heptane from this solution. What is that going to be? What is the equilibrium vapor pressure of a 50-50 molar hexane-heptane solution?
So that's vapor pressure both them together.
There you go. So that's going to be the vapor pressure of hexane plus the vapor pressure of heptane, or the total vapor pressure of this solution. And what does Raoults Law tell us? Raoults Law tells us that the vapor pressure of the hexane is going to be equal to the mole fraction of hexane times the vapor pressure of pure hexane. Okay, the math is simple. You have to figure out what symbols, what the data is telling you. The challenge is following the data. So, what is the mole fraction of hexane?
0.5.
0.5. And the equilibrium vapor pressure of hexane?
51.4 millimeters of mercury.
And what's that?
75.7.
And the vapor pressure of heptane is same?
That's different. The answer.
No, it's the same mole fraction.
Oh, yeah, yeah, yeah.
0.50 times, what is it?
22.85 or 35.
So P total is the sum of those two. Okay? Pretty straightforward. But like I said, you really have to follow the symbols. And what are we dealing with here? This is the partial pressure of the hexane from this solution. It's in solution with heptane. So it's not going to generate this pressure, it's going to only generate that pressure. And here's your total pressure.
So would you say that we like raise the boiling point by putting these two together? Or does that mean like colligative properties? There's less overall pressure than when you have them together? What do you say?
Well, you're raising the boiling point
Of both.
of both of them. The heptane,
Because you have
There's less vapor pressure for both.
less vapor pressure means higher boiling point, right? That's kind of, we could go back to
yeah, that's true.
on
Yeah.
equation.
That's weird.
Okay, so you could say that we're like raising the boiling point of both of them, and which goes back to Chem 2, like colligative properties, that when you mix two things together, you get a higher boiling point.
Yeah, you'd have to heat the solution hotter to reach 1 atmosphere. Yeah.
So if you change the temperature of the closed system, that's going to change the pressure, right?
Yes.
Yes, okay.
Yep. Because then you change the temperature, then you're going to be talking about a different vapor pressure for each one of those at this new temperature.
Okay.
Yeah, it would raise it. So raising the temperature will raise it. Okay. Okay, here is the next equation. This is taking Raoult and Dalton's law together. And let's just see how we get there. This is where we're going to get to. We're going to have an equation that if we want to calculate a total pressure, look at what we're getting at here. We just have the vapor pressure of each one of the pure components times the mole fraction of one of the components, and you can calculate the total pressure of the system. But how did we get down to this? So here's where we want to get to, and this is, what equation number is this? Sorry, I didn't put it on here. It's like equation, I think it's right at the top of that page, isn't it? Is that it? No?
Here it is. 7.17.
Okay, so how do we get here? So Dalton's law tells us that the total pressure of a mixture of gases is really the sum of the partial pressures of all the gases that are present. So the total pressure, Raoults Law tells us that it's going to be equal to the mole fraction of component 1 times the vapor pressure of pure component 1 times the mole fraction of component 2 times the vapor pressure of pure component 2. But we know in a binary system, yeah, Grant?
How much is this equation going to change if we're doing a 3-component system? Or are we not going to be doing 3-component systems?
Well, that's a good question.
Because like I see this equation, these two equations right here would both change, obviously, but I just don't know how it would affect that one.
Yeah, it will make it will certainly snarl up the mathematics a little bit, because let's just go on and then imagine what would happen if we had 3 components. Just keep in mind, in a binary system, x2, the mole fraction of x2 is 1 minus x1. And so you can actually just put that into this equation. And we're almost done here. So let's just at least derive this. And so you get P total equals x1 P1 plus P2 minus x1 P2. So this is going to be P2 plus x1 P1 minus x1 P2 with an asterisk on it. All of these have asterisks on it, by the way. Sorry. And so this is P2 plus P1 minus P2 times the mole fraction of x1. All right, so we're running out of time. So there is the final derivation of that. That's that equation that we had at the top. Equation 7.17. And for Wednesday, why don't you read this problem and label it. What is P1 with an asterisk, P2 with an asterisk, and they want to know what is the composition of the solution. So you need to calculate x1. That will also define x2. You can calculate x2 from x1. All right? So take it that far, and we'll start Wednesday solving that problem real quickly. So bring this set back on Wednesday. I told you I would... does anybody want to start looking at the problems at the end of the chapter?
Like the homework?
Yeah, well, I'll get to it, but if you are curious at all, you could look at these. I don't know that these will end up on these are some that I'm considering for the homework. And that isn't a comprehensive list yet. All right,
I don't know when it's going to be due, the homework.
No, but I'll try to get Chapter 8 or Chapter 7 homework finalized for Wednesday and handed out to you. But if you want to start digging into Chapter 7, that's where to start digging.
Do you want me and Liz to remind you about this? Or?
Let me see if I actually did write that down. I don't think I did. That was one point. That was one point, right?
Oh.
Okay, Liz and Dominic.
Ryan.
Fun fact, no day is a good day. No day is a good day.
All right, I'll try to get that updated quickly.
You call him Dad?
Yeah.
I don't know.
You gotta call your Ari dad. Well, don't call your Ari dad.
Yeah, don't do that.
Don't do that.
Don't call my